Hello, this is Gregory Maxwell, and this lesson in algebra is about solving absolute value equations and inequalities. In order to do this lesson, you must be familiar with the basics of solving equations and inequalities, and those equations you should also be able to solve uh, polynomial equations, quadratic in particular, or factored polynomials, and absolute value, and sorry, polynomial and rational equations and inequalities. Now let us get into some uh, uh, work here. Definition of absolute value. The absolute value of a number is the distance of the number from zero if it's on the two-dimensional number line, or from the origin if it's in a rectangular coordinate system. In some contexts, like in with complex numbers, the absolute value is called a modulus, or it's called a magnitude of a vector. And in those cases, it's basically the distance from the zero complex number or from the zero vector. The absolute value of zero is zero, and the absolute value of a non-zero number is positive. So if the number is negative or if the number is positive, its absolute value will be zero. The absolute value, therefore, is never a negative number. The absolute value is always non-negative. It's either a positive number or it is zero. So for any real number, x, if x is a positive number or zero, the absolute value is just the number itself. For example, the absolute value of 5 is 5. The absolute value of 0 is 0. But if x is a negative number, the absolute value is the negative of x. In other words, you change the sign. So the absolute value of negative 7 is positive 7, or the negative of negative 7, which is positive 7. Now, let's get into the particular situation here. We're going to talk about solving absolute value equations. And I have an example here to illustrate. Solve this equation. Negative 6 times the absolute value of 5x minus 3 plus 7 is equal to negative 35. The first step is to isolate the absolute value on one side of the equals. So we'll use PEMDAS to get the absolute value expression by itself. So first we will subtract the 7 from both sides. So negative 35 minus 7 is negative 42. Then we will divide both sides by negative 6. So negative 42 divided by negative 6 is 7. Then the absolute value is now isolated. What we're seeing here is the absolute value of some number is 7, which means the thing inside the absolute value is 7 units away from 0. That means either this number inside the absolute value is 7 or it's negative 7, because those are the two real numbers that are 7 units away from 0. Generally speaking, if W represents an algebraic expression, say like W could represent 5x minus 3 in our example, if W is an algebraic expression and K is a positive real number, such as 7, then if the absolute value of W is equal to K, that means that W is equal to the negative of K, or the positive version of K. So if 5x minus 3 is equal to, absolute value of 5x minus 3 is equal to 7, that means either this 5x minus 3 is 7 or this 5x minus 3 is negative 7, because those are the two possibilities whose absolute value is 7. So what we will do then is interpret this absolute value equation, this absolute value equaling a positive real number, to meaning one of two things. Either inside the absolute value is equal to negative 7, or inside the absolute value is equal to positive 7. That is, either this number here that we're taking the absolute value of works out to be negative 7, or this number works out to be positive 7, because those are the two numbers that when you take their absolute values, you get positive 7. Now we solve each equation. So we have the two equations here to solve, and we solve it as always. We add 3 to both sides. In this case, we add 3 to both sides. Negative 7 plus 3 is negative 4, and positive 7 plus 3 is 10. And then we divide both sides by 5 in this example. So the answer is either x is negative 4 over 5 or x is 2. And then finally, we check our answers. Always check your answers. Even in those cases where I don't check the answer in this video, you should also check your answers. So let's check our answers. We take this negative 4/5 and we plug it into the original equation. And we just use our calculators, or you can do it by hand. 5 times -4/5 is -4 plus -3 is -7, and the absolute value of -7 is 7. 7 times -6 is -42, plus 7 is -35. So that works out to be the same thing as what's on the right side of the equation. Let's try 2 now. When we try 2, we plug in 2. 5 times 2 is 10 minus 3 is 7. Absolute value of 7 is 7. -6 times 7 is 40. -42 plus another 7 is -35. So it turns out that both answers work. So our solution is -4/5 and 2, because those are the two numbers that make the equation true. Now, what we're going to do is we're going to solve a few examples. So let's start off with a simple example here. Our first example is absolute value of 2x plus 3 is equal to 5. So since the absolute value is already isolated by itself, what we will do is simply interpret the absolute value. This means inside the absolute value is either -5 or it is equal to +5. So 2x plus 3 is equal to -5, or 2x plus 3 is equal to +5. Now we solve each part. We subtract 3 from both sides, and we then divide by 2. So when we subtract 3 from both sides, we get 2x is equal to -8, or 2x is equal to +2, because what we've done is subtracted 3 from both sides in both equations. And then we divide both sides by 2, so x is either equal to -4 or x is equal to 1. And of course, you can check. So please remember to check. I won't show it in here, but I will talk about it in the video. Remember to check. So when you try, well, let me just show it. Now, when we try x equal to -4, we have on the left-hand side 2 times -4 plus 3, that's 8. -8 plus 3 is -5. So that gives you the absolute value of -5, which is 5, and that works. And then let's try the other number. Let's try 1. So when we try 1, we get absolute value of 2 times 1 plus 3, and that's just absolute value of 5, which is 5. So both answers work. So then my solution then is from left to right, -4 and 1. Those are my two numbers that makes the statement true. I'd like to remind you that you can try some of these equations. I recommend that you try some of these equations on your own, or these exercises on your own, and then you can check the answer afterwards. Now, in this situation, we have a little situation here that we have to be careful of, because we have an absolute value that's equal to a negative. An absolute value is never equal to a negative. So since, and let me type this up for the sake of clarity. So what we're saying here is since absolute value of a number is never negative, then no solution. So there is no solution to this equation, because we're saying that an absolute value equals to a -1/2. Absolute value of u minus 2 is equal to a -1/2. That will never be the case, because if inside the absolute value works out to be 0, that would be 0. If inside the absolute value works out to be a positive, that would be a positive answer. And if inside the absolute value works out to be a negative, that would still be a positive number. So no value of u will ever cause this equation to be true. There is no solution. Now, we have another one, relatively easy. It just has fractions to it. So this is not much of a more difficult question than our first example. Again, the absolute value is by itself. It's isolated on one side of the equals. So we interpret that to mean inside the absolute value is equal to the negative of 2, or inside the absolute value is equal to the positive of 2. And just like a side note here, remember from our previous example that we can only interpret this equation this way if the absolute value is equal to a positive. If the absolute value is equal to a negative, then there is no solution. In this case, we solve this equation relatively easily by multiplying by the common denominator, which is 15 in both cases. So I'm going to multiply the left side here by 15, well, both sides by 15. And we'll get a linear equation that's relatively easy to solve. So I multiply x over 3 by 15, I get 5x. And I multiply 2/5 by 15, and that will give me, I believe that is 6. And negative 2 times 15 is negative 30. And then over here, we still get 5x plus 6, but this time we get a positive 30. And now we subtract 6 from both sides in both cases. And then we have 5x is equal to negative 36, or 5x is equal to positive 24. And then we divide. Divide both sides by 5. We get x is equal to negative 36 over 5, or x is equal to 24 over 5. And again, check. I would recommend you check answers. So I'm not going to show that in the notes, but I'll explain it. Negative 36 over 5 multiplied by 1/3 or divided by 3 will be negative 12 over 5. Negative 12 over 5 plus 2 over 5 is negative 10 over 5, which is just negative 2. And the absolute value of negative 2 is 2. If we try 24 over 5, we have 24 over 5 times 1/3 is 8 over 5, and 8 over 5 plus 2 over 5 is 10 over 5. 10 over 5 is 2, and the absolute value of that is 2. So it turns out that both answers work. Both of these are the solutions. So we can then say that the solution is negative 36 over 5, which is a simplified improper fraction, or 24 over 5. Those are the two possible numbers that will work. Let us continue to the next example. In this example, the absolute value is not by itself, so we isolate the absolute value by subtracting 8 from both sides. So let's see what we end up with here. So when we subtract 8 from both sides, we have absolute value of 1 minus 4t is equal to 5. And then we're going to solve that equation. Well, we're going to interpret that equation. What we're saying is the absolute value, the parts inside the absolute value is either equal to negative 5, or the part inside the absolute value is equal to positive 5. So side note here, when you're writing your absolute value bars, make sure that you don't confuse them for a 1, so make them a little taller so that there's less confusion, okay? Now, let's solve this equation. First, I would subtract 1 from both sides because I'm trying to isolate the variable. And then I'll have now negative 4t is equal to negative 6 for one equation, and negative 4t is equal to 4 for the other equation. And then we divide both sides by negative 4. So in this case, t is equal to 6 over 4, which is the same thing as 3/2, or in this case, t is equal to negative 1. And of course, remember to check 4 times 3/2 is going to be 6, and 1 minus 6 is negative 5, and the absolute value of negative 5 is 5. 5 plus 8 is 13. So this one checks out. And then for the other one, plug in negative 1. 1 minus 4 times negative 1 is 1 plus 4, that's 5. And absolute value of 5 is 5 plus 8 is 13. So both check out, both answers are correct. So the solution here is negative 1 and 3/2. I'm just writing them in numerical order from left to right on the number line. Let's do another couple of examples here. This one looks a little bit more involved. This involves absolute value quadratic equations. And of course, as before, isolate the absolute value, which is already isolated, and then we interpret it So this means x squared minus 2x is equal to negative 3, or x squared minus 2x is equal to positive 3. Now let's see if we can solve these equations. So it's a quadratic equation, and that's something we should already know how to do. We add 3 to both sides on the left side, and we subtract 3 from both sides on the right equation, and we have a quadratic equation here. And let's see if we can factor this equation. This equation, we need two numbers that multiply to be positive 3 but add up to be negative 2. And it appears that there is not a number that we can come up with that will pair of numbers that we can come up with that will work with that. So what we're going to have to do is use a quadratic formula. So we do x equals to negative b plus or minus the square root of b squared minus 4 times a 4 times a times c. And then we'll divide both sides by the 2 times a. So when we do that, we get x equals to 2 plus or minus the square root of 4 minus 12 and over 2. And we see here that we end up with something that is not a real number, because the square root of negative 12 is a complex number. So we'll just say then that since we're talking about absolute values and we're going to stick to real number solutions, we write no real number solutions for this part. So the one equation didn't give us any real numbers. Let's go over to the other equation. For the other equation, we're now going to try to solve this one, and it turns out that this one can be factored. We need two numbers that multiply to be negative 3, but when you add them, you get negative 2. Those numbers, of course, are negative 3 and positive 1. So when we set each part equal to 0, we end up with x equal to 3 or x is equal to 1. So the only answers that seem to work here are 3 and 1. Now we can check it. When we check it off, we do 3 and negative 1, sorry. We go 3 squared minus 2 times 3. 3 squared is 9. 2 times 3 is 6. So 9 minus 6 is 3. Absolute value of 3 is 3. And then negative 1 squared is 1, and negative 1 times negative 2 is positive 2. 1 plus 2 is 3. Absolute value of 3 is 3. So our solution is negative 1 and 3. Now, another equation, similar approach. So the absolute value is already isolated, so we just set each part equal to the negative or the positive, because those are the only two numbers that when you take their absolute values give you 2. In this case, it's a quadratic equation. We add 2 to both sides, and we have a nice factorable equation here, which I can just factor out x. First rule of factoring is the least common factor, the greatest common factor, sorry. And x, in this case, x is equal to 0 or x is equal to negative 3. Over here, subtract 2 from both sides, I get x squared minus plus 3x minus 4 equal to 0. And that also can be factored as x minus 1 and x plus 4. So I set each part equal to 0, get x equal to negative 4, or x is equal to 1. So now we have 4 possible answers to try. I try 0. 0 squared plus 3 times 0 times plus negative 2 is negative 2. Absolute value of negative 2 is 2. So that one works. Let's try the next one. The next one is negative 3. The square of negative 3 is 9. And then 3 times negative 3 is negative 9. 9 plus negative 9 is 0. Absolute value of negative 2 is 2. We try negative 4. Negative 4 squared is 16 plus 3 times negative 4, that's 16 plus 12. That's so what's negative 12? That's positive 4. Positive 4 minus 2 is 2. And so the absolute value of 2 is 2. That works. And then 1. 1 squared plus 3 times 1 is 4. 1 plus 3 is 4. And then 4 minus 2 is 2. Absolute value of 2 is 2. So it turns out that all 4 answers worked. So our solution for this quadratic inequality is from least to greatest, from left to right, -4, -3, 0, and 1. Okay, so of course I would encourage you to practice some more equations on your own. I'll do a couple more examples and then we go to solving uh, absolute value inequalities. Now these equations are a little different because they are not linear. They are absolute. There's a rational here, and in this case we have two absolute values, one on either side. So this is going to be a little bit more involved. So in this case, the absolute value is already isolated, so we're going to interpret it. 2x plus 1 over 3x plus 4 is equal to -1, or 2x plus 1 over 3x plus 4 is equal to +1. And if you recall, since we have a rational inequality here, we have to bear in mind that the denominator is not allowed to be 0, so x cannot be -4/3, which I got from setting the denominator equal to 0 and solving for x. So as long as we don't get -4/3, we can check the other answers. In this case, we can simply cross multiply both sides. Since it's an equation, we would not be able to do that if it was an inequality, but we can do it if it as an equation. So I'll get 2x plus 1 is equal to negative times -1 times 3x plus 4. And over here, we have 2x plus 1 plus 1 is equal to 1 times 3x plus 4. So that works out to be nice. We distribute the negative on the left side equation. We get -3x minus 4, and we'll just solve that equation. We'll add 3x to both sides, and we will subtract 1 from both sides. And so we end up with 2x plus 3x is 5x, and -4 minus 1 is -5, which means x is equal to -1. Or for the right side, we just subtract 2x from both sides and subtract 4 from both sides, and we end up with -3 is equal to x. So then we have two possible answers here. X is either equal to -3 or x is equal to -1, neither of which is restricted. Let's try -1. When I try -1, 2 times -1 is -2. -2 plus 1 is -1. 3 times -1 is -3 plus 4 is +1. -1 divided by +1 is -1. Absolute value of -1 is 1. So -1 works. Then let's try -3. 2 times -3 is -6. -6 plus 1 is -5. 3 times -3 is -9 plus 4 is -5 again. So we have -5 divided by -5 is +1. Absolute value of +1 is 1. So both answers work. Since both check out, our solution then is set -3, -1. Now, last example before we go to the next concept, we're talking about solving two absolute values. Now, just think carefully here. If an absolute value of one number is equal to the absolute value of the other number, there are only two possible situations that can occur. That means either both numbers are the same, because your absolute values would be the same in that case, or one number is the opposite of the other. One number is the negative of the other. Those are the only two possibilities for real numbers. If two real numbers have the same absolute value, that means they're the same number, or one is the negative of the other. So that's what we did. Either x squared minus 2x is equal to x squared plus 6, or x squared minus 2x is the negative of x squared plus 6. And then we just solve. For the left side equation, we can just subtract x squared from both sides. And we end up with -2x equal to 6x. And of course, we can solve that equation by subtracting or adding 2x to both sides. And that will give us 0 is equal to 8x. And of course, if we divide both sides by 8, that would mean x is equal to 0. On the other side, we distribute the parentheses, the negative into the parentheses. So we'll have negative x squared minus 6x. So we end up with negative x squared minus 6x, which of course now we have a quadratic equation. We can add x squared to both sides and add 6x to both sides. And when we do that, we have 2x squared plus 4x is equal to 0. I factor out a 2x, and because the first rule of factoring is to seek for the greatest common factor, I set each factor equal to 0, and I solve for x. And when we do that, one value is 0 and the other value is -2. Of course, we have to try all of them. Both answers gave us 0, so basically we only have 2 answers to try. We plug in 0. 0 squared minus 2 times 0 is 0, and the absolute value of 0 is 0. And then 0 squared plus 6 times 0 is also 0, and the absolute value of 0 is 0. So 0 clearly works. And then we try -2. The square of -2 is 4, minus 2 times -2, that's 4 plus 4, that's 8. Absolute value of 8 is 8. Over here, the square of -2 is 4, -2 times 6 is -12, 4 plus -12 is -8. Absolute value of -8 is 8. So both sides work out to be the same. So now our solution then is -2, -2, comma 0. All right, let us go on to our next concept, which is solving absolute value inequalities. Absolute value inequalities. So when solving absolute value inequalities, please bear in mind again that the absolute value is the distance from 0. This is very important when we're solving absolute value inequalities because the way we interpret the absolute value inequalities changes in this situation. It's not the way that we did the equals, it's a modification, which is a little bit more technical. So we're going to have two different cases that we have to consider here. As with the equals, we need to isolate the absolute value on one side of the inequality. So we have one example here, my first example, -3 times the absolute value of 2x plus 5. That quantity plus 7 is greater than or equal to -8. To isolate the absolute value, I will subtract 7 from both sides, and then I will divide both sides by -3. So when I subtracted 7 from both sides, I got -15 on the right side. And when I divide it by -3, I got a +5. But because I divided by a negative, the absolute value, the inequality switches direction, as always happens when you multiply or divide by an inequality by a negative. Now, first case is if you have an absolute value that's less than or equal to a positive number. So I'm going to use this rule here. If it's less than a positive number, that means the absolute value, the thing that you're finding the absolute value of is closer to 0 than that number. So that 2x plus 5 is closer to 0 than 5 units away. So what we do is we look for the two numbers that are 5 units away from 0. Namely, those numbers are -5 and +5. That means this 2x plus 5 is closer to 0, which means on the number line, it's between them. Here's what it looks like. Let's say my algebraic expression w is less than k, k being a positive number. What I do is I put my two k's, one is -k and one is +k. That means w must be somewhere in between those two numbers. So if my w is 2x plus 5, if my w is 2x plus 5, and my k is 5, then that means 2x plus 5 is closer to 0 than whatever is 5 units away from 0. Those numbers that are 5 units away from 0 are -5 and +5. So this expression must be somewhere in between those two numbers. And that is the reason that when the absolute value is less than a real number, then it's a compound inequality where we're saying it's both greater than the negative and less than the positive. Now, let's continue solving this compound inequality. It's a simple inequality. All we have to do is isolate the x in between. So we just subtract 5 from all parts in this example. and then we divide all parts by 2. Dividing all parts by 2 doesn't reverse the inequality because we're dividing by a positive. And so our solution is -5 is less than or equal to x, which is less than or equal to 0. So what we're going to do now is graph the solution and check. Let's start by checking. We have the correct answer should be in between -5 and 0, and -5 and 0 could work. If I try -5 or try 0, I should get the same thing on both sides of the equals. So let's try -5. 2 times -5 is -10. -10 plus 5 is -5. The absolute value of -5 is 5. -3 times 5 is 15. Is -15. -15 plus 7 is -8. -8 is equal to -8, so that makes the statement true. Greater than or equal to includes equal to. Let's try 0. Try 0. 2 times 0 is 0. 0 plus 5 is 5. Absolute value of 5 is 5. -3 times 5 is -15. -15 plus 7 is -8 again. And that's allowed. Now let's try a number that's in the correct region and see if it gives us a true statement. We try -2. -2 on the left side of the inequality is -3 times 2 times -2 plus 5, and then that quantity plus 7. The absolute -2 times -2 plus 5 is 1. So the absolute value of 1 is 1. 1 times -3 is -3. -3 plus 7 is 4, and 4 is definitely greater than or equal to -8. So a number in the region works. Let's try a number in the region that should not work. That means it should give us a false answer. We try 2. I try a number that's not in between here. You could try a number to the left or a number to the right. I chose a number to the right side. I try 2. I plug in 2, and when I work it out, I get -20. But -20 is not greater than -8. So that confirms that when we chose a number not in the correct region, it didn't give us the correct statement. So this indicates that we are probably quite likely correct. So what we do now is we graph the solutions. We graph our two numbers. X should be between the numbers going from left to right, and then it should be brackets opening toward the shaded region because there's a bar there. The interval notation, of course, then would be bracket -5, comma 0. Now let's try the other example. The next example is solve the inequality 2 times the absolute value of 3x minus 4 minus 15 greater than or equal to -3. So as with the previous example, we isolate the absolute value on one side of the inequality. So we're going to add 15 to both sides, and then we're going to divide by 2, and that will give us absolute value of 3x minus 4 is greater than or equal to 6. Now in this case, the absolute value is greater than or equal to 6, which means whatever is inside the absolute value is further away from 0 than 6 units. So that means it's either to the left of -6 or to the right of 6, because -6 is 6 units away from 0. Anything to the left of that is further away. And +6 is 6 units away from 0. Anything to the right of that is further away. So when we see an absolute value of an expression greater than a positive number, so if the absolute value of an algebraic expression is greater than a positive number, that means whatever is inside the absolute value is further away than k units. That means it's to the left of the negative or to the right of the positive. Here's a graph to illustrate what's going on. Let's say k here is my number, in this case 6. So this would be -6 on the left, +6 on the right. Then inside the absolute value should either be to the left or to the right of -6 all the way to -infinity, or to the right of +6 all the way to +infinity. Any number on the right side or any number on the left side. In the previous case, it had to satisfy both conditions. It had to be in between. But in this case, either case is fine. So now that we have that inside the absolute value is either less than negative or equal to -6 or greater than or equal to +6, we can now solve each inequality. We're going to add 4 to both sides in both inequality and divide both sides by 3. And then we have two possible regions here. We have x is either to the left of -2/3, that means less than or equal to -2/3, or to the right of 10/3, starting from 10/3 to the right. So if we try a number on the left side of negative 2/3, that will work. We try negative 2, which is on the left side of negative 2/3. It turns out to work out to be 5, which is definitely greater than or equal to negative 3. If I try a number to the right of 10/3, 10/3 is 3 1/3. So if we try 5, that would be to the right of 10/3. I try that number and it works out to be positive 7, which is also greater than negative 3. So when I try the number to the left of negative 2/3 and the right of positive 10/3, both work. So whether I choose a number to the left hand side or on the right hand side, either one will work. To graph that, I would graph the negative 2/3 to the left and shade that with a bracket because it's a less than or equal to, and positive 10/3 to the right because it's a greater than or equal to and a bracket. So my solution then is the region to the left of negative 2/3 or to the right of positive 10/3. In interval notation, negative infinity to negative 2/3 bracket union 10/3 to infinity. And remember, infinity always uses parentheses. All right, let's do a few more examples, and then we'll talk about some important points to remember. Now, in this example, we just simply isolate the absolute value. So I'm going to isolate the absolute value of x plus 4 by subtracting 3 from both sides, and we get absolute value of x plus 4 is less than 2, less than 2. And when just as a side note again, make sure your absolute value bar does not look like a 1. Now that the absolute value is less than 2, we're saying that this region is closer to 0 than 2 units. What numbers are close to are 2 units away from 0? Those numbers are 2 and negative 2. And my x plus 4 region must be closer to 0 than those numbers. That means my x plus 4 must be some number that's in between these guys, strictly in between. So that means x plus 4 has to be between negative 2 and positive 2. This is a nice simple compound inequality. I just subtract 4 from all parts, and then I have my answer. Negative 6 is less than x, which is less than negative 2. So if I choose numbers between negative 6 and negative 2, those will work. But if I choose numbers that are not between them, those numbers will not work. So I'm going to leave you to check the solution here. And I'm just going to graph the solution set. The marker on the left is negative 6. The marker on the right is negative 2. I shade between them because x is between them from left to right. And we use parentheses because it's a strict inequality. So my interval notation then, is negative 6, comma, negative 2. Oh, made an error here. Parentheses, negative 6, comma, negative 2. And if I'm using set notation, we could say it's a set of all numbers x with a property or such that we can write a colon or bar. X is some number between negative 6 and negative 2. You can check it out as I said. I will check one example in between. So a number between negative 6 and negative 2 is say negative 3. Negative 3 plus 4 is positive. One absolute value of 1 is 1. 1 plus 3 is 4. And 4 is less than 5. So that was a quick check right there. So this one here, by the way, is the graph. And I drew the shaded region above the graph so it's visible. Now let's go on to the next example. In this case, the absolute value has a negative in front of it, so we have to isolate it by multiplying both sides by negative 1. When I multiply by a negative, the absolute value um, stays, but the inequality reverses. So we have absolute value of 2x minus 1 is less than or equal to 3. So we have 2x is between 2x minus 1 is between -3 and 3 for the same reason as we had over here. It's less than. And then we just solve it as we did before. We add 1 to both all parts, and then we divide by 2. So we end up with -1 is less than or equal to x, which is less than or equal to 2. And then you can check a number like 0, and you'll see that the negative of -1, absolute value of -1 is 1, and -1 is greater than or equal to -3. If you try -1, you should get 3, and if you try 2, you should also get 3. So my graph of my solution set, is -1 to 2. We're shading in between. We use a bracket. And so my interval notation for my solution is bracket -1, comma 2 bracket. All right. Let's go on to another example. In this case, to isolate the absolute value, we simply add 7 to both sides. So I'm going to add 7 to both sides, and the absolute value of 4x is less than 5. And we have a less than situation again. So we isolate the absolute, we put the absolute value in between the negative and the positive, and the reason again is for what I demonstrated over here. It's between two numbers that are 5 units away from 0. Those numbers are -5 and 5. And then I solve for x. I subtract 1 from all parts, and then I divide by the -4. But whenever I divide by a negative, remember the inequality gets reversed. All the inequalities get reversed. So you have to make sure you pay attention to those little nuances here. So when I reverse inequalities, I get -6 over -4 is 3/2. That reverses that inequality. X is by itself because we divided the -4, and 4 divided by -4 is -1, which makes sense. 3/2 is greater than -1, so we can turn the whole thing around saying -1 is the one that should be on the left because it's the less, and 3/2 should be on the right because that's the greatest there with x in between. And I'm leaving you to check the solutions for that one, and we're just going to graph the solutions as well as write the interval notation. So the two numbers we'll put on the graph are -1 and +3 over 2. And of course, we shade between because x is between, and it's a strict inequality, so we use parentheses. So my interval notation for my solution is -1, comma 3/2, both with parentheses. Okay, now I already explained the other example here with when the absolute value is greater than a positive number. Let's try a couple of examples of those. In this case, absolute value of 3x plus 4 is greater than or equal to 2. The absolute value is already isolated. What this is saying is, if we were to look at the number line, I'll call this a little preliminary sketch, a little prelim. We need numbers that are further away from 0 than 2 units. The two numbers that are 2 units away from 0 are -2 and 2. So we need numbers on the left side or on the right side. So we need to take 3x. Left this out is either on the left side of -2, to the left of the negative, or to the right of the positive. So that means 3x plus 4 is either less than or equal to negative 2, or 3x plus 4 is greater than or equal to 2. It is good to think of the greater than or equal to as to the right or to the left, respectively, because it helps you to visualize what's going on and helps you to understand the math a little better. We solve each inequality as before, subtract 4 from both sides, and then divide by 3. And then we plot the numbers on the number line. And again, it's an OR, so we don't need an overlapping region. We just need whatever works. Now, the numbers in order from left to right are negative 2, which is to the left of negative 2/3. And this inequality says we shade to the left. And the other inequality says we shade to the right. And since that's a greater than or equal to, we use brackets that open to the directions that we shade. So my solution in interval notation, is parentheses negative infinity to negative 2 bracket or, which is that union symbol, negative 2/3 to infinity. And I'm going to leave you to check the solution here. You can try any number. You should try a number in both regions. So you try negative 3, for example. It should work. Negative 3 times 3 is negative 9 plus 4 is negative 5. Absolute value of negative 5 is 5, which is greater than or equal to 2. If I try 1 or even 0, if I try 0, which is on the right side of negative 2/3, we get 3 times 0 is 0, and then plus 4 is 4. Absolute value of 4 is 4, which is greater than or equal to 2. So both numbers work. This number is very similar to what we just did. Again, we need numbers that are to the left of the negative or to the right of the positive. To the left of the negative or to the right of the positive. So I solve each inequality. In this case, I'm going to subtract 2 from both sides. So negative 3x is less than negative 3. And over here, I subtract 2 from both sides. I get negative 3x is greater than negative 1. Divide both sides by negative 3. When I divide by a negative, the inequality reverses. So we end up with x is greater than 1 or x is greater than, is less than, 1/3. And so again, we have our two solutions there. And as before, I'm going to leave you to check those solutions. I'm going to write this down here. Remember to check. Remember to check. All right. So let's graph our solution. So our solution then is numbers to the right of 1. So 1 would be on the right-hand side here, actually. If you look at the two numbers in order, 1/3 is a number that's smaller than 1, and they're positive. So 1/3 is to the left and 1 is to the right. So we're taking numbers to the right of 1, and it's parentheses, we'll shade in the direction of that, and to the left of 1/3. And then solution then is negative infinity to 1/3 parentheses or parentheses 1 to positive infinity. The process is the same. You just have to be patient and work step by step. Now, let's go quickly to the next example here. Isolating the absolute value, we get negative absolute value of x plus 1 is less than half minus 3. Now, half minus 3 is just a simple fraction here. So you're going to get negative 5/2 because that's half minus 6/2. 2. Then when we multiply both sides by -1 to get the absolute value by itself, then the negative 5/2 becomes a positive 5/2. And that, the absolute value now, is the absolute value of x plus 1 is greater than 5/2. And as with the other two examples we just did, we just say that means x plus 1 is less or to the left of the negative, or x plus 1 is to the right of the positive. X plus 1 is less than -5/2, or x plus 1 is greater than 5/2. We subtract 1 from both sides, so we get x is less than -7/2, or x is greater than 3/2, which you can check on your calculators. We can try a number to the left of -7/2, say -10. Try -10. -10 plus 1 is -9. Absolute value of -9 is positive 9. 3 minus 9 is -6, which is definitely less than half. And you can also try a number to the right and get a similar answer. So my solution then, let's graph it first, or graph. So the graph has the two markers, -7/2, -3.5, or 1.5, 3/2. We're shading to the right of 3.5 and to the left of -7/2, and both of them use parentheses. And so my interval notation, my answer for my interval notation is from the left, -∞, all the way to -7/2, or 3/2 to positive infinity. Now, before I do the last set of examples here, I want to point out a couple of things that you need to notice about solving inequalities. First of all, if you want to find an absolute value of that is equal to a negative, so if the absolute value is equal to a negative, then you have no solution. We encountered one earlier. So if we're solving this equation, we isolate the absolute value. We subtract 2 from both sides, divide both sides by 6, and see what we get. We get absolute value of 8x minus 11 is equal to a -5. Absolute value is never equal to a negative, so this one has no solution. Also, if an absolute value is less than a negative or less than 0, then there's no solution. So if I have an absolute value inequality here, I isolate the absolute value, add 4 to both sides, and divide by 5. I get absolute value of x plus 9 is less than -2. Absolute values are never less than negatives. Absolute values are only positive or 0. So this answer, there's no solution to this inequality. This one does not work. Another example, what if the absolute value is greater than or equal to a negative? If your absolute value is greater than or equal to a negative, or if it's greater than or equal to 0, that means it's always true. So if I'm solving this inequality and I have absolute value of 9x minus 1 plus 5 is greater than or equal to -8, all I do is subtract 5 from both sides, and I get an absolute value that's greater than or equal to -13. But absolute values are always positive, and positives are always greater than negative numbers. So this statement is always true. Because this statement is always true, that means whatever I use for x will work. The solution then is all real numbers, which is written as -∞ to infinity. Now, if an absolute value is less than or equal to 0, there's only one thing that will work, and that's if the inside of the absolute value gives you 0. So if absolute value of 5x plus 20 is less than or equal to 0, this thing will never be negative, so the only thing it can be is 0. So we just set the inside equal to 0, solve for x, and the only number that will work is -4. Let me back up here a bit because that one went off a little quickly. So one more time so that you can see it. I would recommend you pause the video and look at those special situations. And now let's go on to a few examples. And once again, I recommend that you try the examples on your own before I do it and then check the answers. So for this one, the absolute value of -4x is just same as 4x. But it's the same as the absolute value of 4x. They give you the same thing. The absolute value of a negative is the same as the absolute value of the positive. The absolute value of -5 is just 5. and then we have less than or equal to 1. We isolate the absolute value. Absolute value of 4x is less than or equal to negative 4, and that's because I subtracted, 5 from both sides. But an absolute value is never equal to a negative, never less than a negative. This statement is never true. An absolute value is never equal to a negative and is never less than a negative. So that means this inequality has no solution. And of course, you write no solution with a circle with a slash through it. Let's go on to this next example. For this next example, I subtract 5 from both sides to isolate the absolute value. And when I subtract 5 from both sides, I get absolute value of x minus 1 is greater than half minus 5 is negative 9 over 2, negative 4.5. This is saying an absolute value is greater than negative. An absolute value is always greater than a negative. Absolute values are positives, and positives are always greater than negatives because positives are to the right of negatives on the number line. So this statement is always true. And because the statement is always true, whatever value of x I use, it will still give me a solution. So then my solution then is all real numbers from negative infinity to positive infinity. I don't have the space to draw the the uh, the number line here. Let me see if I can draw it. I doubt it, but we'll see here. And then draw the number line, and then you simply shade the whole number line. The whole number line is shaded because all real numbers work. Okay, so let's take a look at the next example. This one looks a little complicated, but it's not really. It's just fractions. It's a linear equation, a linear inequality. And we will go about it as before. The inequality, absolute value is isolated on one side. It's a greater than sign. So what we're saying is that 2x minus 3 over 2 plus 1/3 is further away from 0 than 1 unit, which means it is to the left of -1 or it is to the right of +1, because numbers to the left of -1 and numbers to the right of +1 are more than 1 unit away. They have absolute values that are greater than 1. Now, we're going to solve this inequality. We can simplify it by just multiplying both sides by the common denominator, which is 6. So we're going to multiply both sides of the inequality by 6. Since we're not multiplying by a variable, then we don't have a problem here. So when we multiply by 6, we end up with 3 times 2x minus 3 plus 2 is less than -6 on the side. And on the other side, we have 3 times 2x minus 3 plus 2 is greater than +6. Because again, we're multiplying each term by 6. Each term by 6. I distribute the parentheses, and once I distribute the parentheses, I combine like terms and solve for the variable. So we have 6x minus 9 plus 2 is less than -6. -9 plus 2 is -7. You add 7 to both sides, we get 6x is less than 1, which means x is less than 1/6. And then for the other side, we have 6x minus 9 plus 2 is greater than 6. And then I add -9 plus 2 is 7. Add 7 to both sides, we get 13. So 6x is greater than 13. So that means x is greater than 13 over 6. So my two inequalities now, it's an or because of the way we split the inequality. Either we're looking at numbers to the left of 1/6 or to the right of 13 over 6. And if you check those numbers, 1/6 and 13 over 6, you'll realize that they will give you the same thing on both sides of the expression, one of the inequality. What's on the left side would equal to what's on the right side. If you try 1/6, 1/6 will give you a -1 inside the absolute value, but the absolute value of 1, -1 is 1. And if you try 13 over 6, that will give you a +1 inside the absolute value. And the absolute value of 1 is 1. But of course, since it's not a greater than or equal to symbol, we use parentheses for my boundaries. And we're going to shade the regions that correspond to the inequality. And so now our solution, reading from left to right, is -infinity to 1/6 union parentheses 13 over 6 to infinity. And that's the answer to that question right there. Let's move on to the next example. This one looks a little bit tricky because you have a variable inside and outside the absolute value, but that's fine. We'll just approach it the same way. We're saying the absolute value of a number is the same as 4 times x minus 5. That means either the number, the stuff inside the absolute value, is equal to 4 times x minus 5, or that that number inside the absolute value is the negative of 4 times x minus 5. Just as we did with the other numbers, you just have to take it a step at a time. So either the inside the absolute value is equal to outside, or it's equal to the negative of outside, because a number and its negative both have the same absolute value. So then we solve. We're going to, of course, distribute the 4, because we're going to have to get the x's together, and then over here we'll distribute the -4. When we do the left side, we get 5 minus 2x is equal to 4x minus 20. And if on the right hand side over here, we're going to have 5 minus 2x is equal to -4x plus 20, because we're distributing a -4. Then we combine the variables together. Since the 4x is positive and the 2x is negative, I'll just add 2x to both sides. And at the same time, to get the x's by itself, I'm just going to move the -20 to the other side by adding 20 to both sides. When I do that, I would get 25 is equal to 6x, which I can then solve for x, and that gives me x is equal to 25 over 6. And we'll check that in a minute. On the other side, we're going to move the -4x to the left side by adding 4x to both sides, and I'm going to get rid of that -5 by subtracting that 5 by subtracting 5 from both sides. And now that gives me 2x is equal to 15, which means that x is equal to 15 over 2. Now, of course, we have to check our answers because we don't know if any extraneous solutions showed up. So what we're going to do now is check. And to check, we're going to do, first we're going to try x equal to 25 over 6. And you can just use your calculator here. We're going to substitute 25 over 6 for x. So the absolute value of 5 minus 2 times 25 over 6. And we'll see that equals to 4 times 25 over 6 minus 5. When we work out the left side here, and again you can do it on a calculator, you'll see that inside the absolute value works out to be -10 over 3. And on the right side here, it turns out that this whole expression works out to be -10 over 3 as well. The problem is the absolute value of -10 over 3 is +10 over 3. So these two things are not the same. One is positive and the other is negative. So in reality, this is not a solution. This statement is incorrect. So we have to say that doesn't work, which means this is not a solution. All right, so let's go on to the next number to check, which is 15 over 2, the other possible solution. We plug it in as before. 5 minus 2 times 15 over 2. Absolute value of that is equal to 4 times 15 over 2 minus 5. work this out, that gives you negative 10 inside the absolute value. And of course, the absolute value of negative 10 is 10. And on this side, it turns out that this works out to be 10 as well. So the left side and the right side here work out to be the same number, which means 15 over 2 is a legitimate solution. So our solution then is just the number 15 over 2. That was the only number that gave us the correct answer on both sides. Just always remember to check your solutions. Now we will go on to another example. A couple more sets of examples. This one is quite involved, so we're going to take a little time with this one. We have an absolute value of a quadratic greater than 12. Well, it's greater than, and the absolute value is by itself, so we just say, oh, well, that means either x squared plus 2x minus 36 is to the left of the negative 12, or x squared plus 2x minus 36 is to the right of positive 12. So we solve these two quadratic inequalities, which is a prerequisite for this concept. We get them into standard form. So I'm going to subtract 12 from the right equation in the right inequality, and I'm going to add 12 on the left inequality because of how they were set up. So we have x squared plus 2x minus 24 is less than 0. And over here we have x squared plus 2x minus 48 is greater than 0. And in this case, we can factor it and find our markers for this one. This is x plus 6 and x minus 4. And in this case, it factors to be x plus 8 and x minus 6. So when you solve both of these inequalities now, what we do is you simply put a pair of markers that represent what would happen if it was equal to 0. So my two markers here on the left equation, the markers are x equal to negative 6 and x equal to 4. And over here, the markers are x equal to 8 and x is equal to 6. And then what I would do is try numbers around them. So I'm not going to show what numbers I'm going to try. I'm just going to tell you which numbers we're trying and then plug them into the various expressions. So for this one, for example, I'll try a number to the left of negative 6, say negative 10. Negative 10 squared is 100 plus another negative 20, that's 80, minus 24, that's definitely a positive number, so we're going to get a positive there. I try a number between negative 6 and 4, say 0. When I plug in 0, I get a negative, because that cancels and leave you, that disappears and leaves you with a negative 24. And if I try a number to the right of 4, say 5, or even 10 again, let's try 10. 10 squared is 100 plus another 20 is 120 minus 24. That's definitely going to be a positive number. And since this is looking for the less than values, we're going to use a region. We're going to use a region that is negative because it's a less than. And then over here, same deal. Try a number to the left of negative 8, say negative 10. Try it up here. Negative 10 squared is 100 minus 20 minus 20 is 80. 80 minus 48 is definitely going to be a positive number. And then we need a number between. We try 0. That gives us a negative. And a number to the right of 6, 10 again. 100 plus 20 is 120 minus 48, positive. And this one is only looking for the positive regions. So we're going to shade to the left of -8 and to the right of 6. And this says wherever these, what is an OR, so whatever works over here and whatever works over here should work. So let's draw them all on the same number line and see what it looks like. I'm going to call this my preliminary number line because it's not my real number line, not my actual graph. So we have -8, -6, +4, and +6. And this says we are shading between -6 and +4. This says shade to the left of -6 and -8 or to the right of 4. So that means those regions that are shaded, it turns out this can be my graph. So I can just erase prelim and write graph since I don't have any overlaps. And anything in these regions work because that's an OR. And our OR says not where it overlaps, but whatever works for a region. So my interval notation then for my solution would be -infinity to -8 union -6 to 4 union 6 to infinity. And moving on to the next example. All right, let's take a look at this next example. As you can see, I made an adjustment to the example. There was some missing stuff. The less than or equal to 3 was missing. So now let's proceed. And in this case now, since it's less than or equal to 3, that means we're saying what is inside the absolute value is between 3 and its negative. Now, this one is going to involve quite a bit of thinking. So what we're going to first do is combine these, well, we're going to split this up into two things. We're saying that -3 has to be the x over 2x minus 1 has to be to the right of -3 and it must at the same time be to the left of 3. So we do not cross multiply when we're solving absolute value inequalities, or when we're solving rational inequalities. We get 0 on one side, so I'm adding 3 to both sides here, which I'll write as 2 over 1, sorry. And then, and this one here, I'm subtracting 3 from both sides, which I will write as 4, sorry, -4 over 1. And then I combine the fractions. So we have x plus 2 times 2x minus 1 over 2x minus 1. And I combine that fraction and simplify the numerator. X plus 4x is 5x minus 2 over 2x minus 1. And over here, and again, notice the word I'm writing now is and not or, because in this case, both statements must be true at the same time. So we have x minus 4 times 2x minus 1 over 2x minus 1, and that should be less than or equal to 0. So we're saying here that x minus 8x is -7x plus 4 over 2x minus 1 is less than or equal to 0. So my markers here for my numerator, my marker is x is equal to 2/5, and that will use a bracket because it's a greater than or equal to, and my denominator marker for this one is x is equal to 1/2, and that's a parenthesis because that's in the denominator. And for the other fraction, the marker is x is equal to 4/7. That's also a bracket. and the other marker is x is equal to half, which is um, a parenthesis. All right, so we'll need a little bit more space to complete this question. So let me just create a little bit more space here. All right, so as I said, this question would be a little bit involved, so let's make sure we can have enough space to complete it. So let's move on to the next part of this, which is finding the solutions for each of these. So I'm going to just draw a little arrow here, and I'm going to draw my number line. I'm going to put my markers, which are 2/5 and half, which half is to the right of 2/5. You can check that in a calculator. And this is for the fraction 0 greater than or equal to 5x minus 2 over 2x minus 1. And now if I try a number to the left of 2/5 like 0, I get negative over negative, which will give me a positive. And if I try a number to the right of half like 1, I get 5 minus 2 over 2 minus 1, which is positive. I try a number in between them, a number that's in between 2/5 and 1/5 and 1/2. It's a little tricky. So what you do is you average them out. So if we add 2/5 plus 1/2, and then divide that number by 2, and that will give us 0.45, which is 9 over 20. So then you try it. 5 times 0.45, or 5 times 9 over 20, minus 2, that's a positive 1/4, and 2 times 0.45 minus 1, that gives us a negative number. So positive divided by negative is a negative. And this one's only the positive region, so we would shade the region to the right and the region to the left. Now, for the other one, this we will do right here. So that graph now is for negative 7x plus 4 over 2x minus 1 is less than or equal to 0. So now we're looking for negative numbers. So my markers are 4/7 and 1/2. Wow, it's cutting it real close here. 4/7 is to the left of 1/2. 4/7 is to the left of 1/2. So, oh, my apologies. 1/2 is to the left of 4/7. Sorry about that. 1/2 is to the left of 4/7. Please check that on your calculator. The way I know is because 4 is more than halfway to 7. Halfway to 7 is 3.5. So 4 over 7 is more than halfway that. So 4/7 is more to the left. So I try 0. I plug in 0 to the left. I get a negative. I plug in something to the right of 4/7 is like 1. Negative 7 plus 4 is negative 7. And then 2 minus 1 is positive 2. Negative 7 divided by positive 2 is negative. And once again, I average out those numbers and try that number. 1/2 plus 4/7 and then I divide that number by 2. And that's 0.535. 0.57. So let's try 0.533. So we can do 0.53. So I do -7 multiplied by 0.53, then plus 4. That gives me a positive 0.29, and 2 multiplied by 0.53 minus 1 gives me a positive 0.06. So we have a positive divided by a positive, and this says we want the the negative regions. So I'm talking about the regions to the right of 4/7 and to the left of half. Now for my overall solution, this one is a bit involved. You have to take it a step at a time. Overall solution is where they overlap because it's an and situation. So I'm going to draw the number line now and look at where they overlap. And my numbers in question are 2/5, 1/2, and 4/7. The first region was 2/5 to the left of 2/5 and to the right of 1/2. The next solution was to the left of 1/2 and to the right of 4/7. Therefore, if you look at this solution here where they overlap, let me just write it a little clearer. Where they start overlapping, these guys start overlapping from 2/5 to the left, and these overlap from 4/7 to the right. So my overall solution then, is from -infinity to 2/5, or from 4/7 to positive infinity. I'm going to leave you to check that answer just because of time. Time is almost 90 minutes. So we've been going here for a while. And this is the graph, the final graph. And now for our final example. We're solving this complicated looking inequality here, and we're going to go through all of that right now. Let's take it a step at a time. We'll remove that bar. We'll need the whole space for it. So we have an absolute value as before. So it's an absolute value inequality. We're going to set it, the absolute value, on one side of the inequality. So absolute value of x squared minus 2x plus 3 is less than 7 because we are subtracting 5 from both sides. And now, since it's a less than or equal to, we're saying that what's inside the absolute value, what is inside the absolute value is between -7 and 7 because it's closer to 0 than 7 units. Now, this is a little tricky here because it's not a linear compound inequality, it's a quadratic. So what we're going to do is have to interpret it the correct way. We're saying that -7 is less than or equal to x squared minus 2x plus 3, and this is an and now, not an or, an and at the same time x squared minus 2x plus 3 is less than or equal to positive 7. So now we can solve both of these inequalities. So I'm going to start off with the first one here. So I have 0 is greater than or equal to x squared minus 2x plus 10. The reason I have that is I add -7 to both sides. I add positive 7 to both sides so that we can get the inequality equal to 0. And then I'm going to find the markers for this inequality by solving the corresponding equation. X squared minus 2x plus 10 is equal to 0. Turns out that this can be factored. X minus, well, no, we cannot factor this. We can try to factor it, but it doesn't work. If this were a negative 10, it would be factorable, but it's not. So what we're going to do instead is we're going to use the quadratic formula. So when we use the quadratic formula, we have x is equal to um, negative b, which is negative of negative 2, plus or minus the square root of b squared minus 4 times a times c, and then divided by 2 times a. When I try to solve that, I get 2 plus or minus the square root of 4 minus 40. That's negative 36. And once we have a square root under a negative under the square root, we know that this is not a real number. These will not be not real number answers, which means there is no x-intercept. If there's no x-intercept, that means this expression is always going to be positive or always going to be negative. We just have to check out which one it is. So let's see. We're going to check a number. The easiest number to check, of course, is 0. So when I check x equal to 0, we see that 0 squared minus 2 times 0 plus 10 is positive 10, which itself is greater than 0. So since the expression we want is supposed to be greater than or equal to 0, then that means that this is also all real numbers solution. So the solution then is all real numbers, because whatever number I plug in will work. So the answer for that part would be negative infinity to infinity. That statement is always true. Now let's go to the next one, this one here. We're going to do that on the right side over here. We have x squared minus 2x plus 3 is less than or equal to 7. So we end up with x squared minus 2x minus 4 is less than or equal to 0. And once again, we have a situation where we cannot factor this one, so we're going to just have to solve the quadratic equation. So we end up with x equal to negative b plus or minus the square root of b squared minus 4 times a times c over 2a. And that will give me 2 plus or minus the square root of 4 minus negative 16 is 20 over 2. And with a little simplifying, we get 1 plus square root 5 plus or minus square root 5. Those are actually two numbers. One is a positive and one is a negative. And so my markers then are 1 plus square root 5 and 1 minus square root 5. So when I try those on the number line, I'm just going to put them on the number line here. 1 minus square root 5 and then 1 plus square root 5. Now the square root of 5 is a number that's between, that's pretty close to 2. It's between 2 and 3. If we do it on the calculator here, square root of 5 is 2.236. So 1 minus square root 5 is approximately negative 1.24. So that means our markers are, this marker here is approximately negative 1.236. And then if I add instead for the other marker, that's approximately 3.236. The reason we do that now is so we can check our markers. We can try a number on the left of negative 1.236, say negative 2. I plug in negative 2 into this expression here. I get 4 plus 4 minus 4. That's going to give me a positive number. And then if I try 0, I get negative 4, the number in between. If I try a number to the right of 3.236, say 4. 4 squared is 16 minus 8, which is 8 minus 4. It's another positive number there. And since this inequality is looking for the regions that are less than 0, then the region that is shaded would be the region between those two values. And since that's a less than or equal to, then we use bracket. Now to the more complicated part. These two solutions must satisfy the condition of an and, which means they must overlap. They must overlap. So what I'm going to do then, I'm going to put both inequalities together on the same number line and see where the two regions overlap. For the inequality on the left-hand side, it turns out that that inequality was all real numbers. And then that's what this guy gave us. But this one gave us numbers between 1 minus square root 5 and 1 plus square root 5. Those are the numbers that we have right here. So where do they start overlapping? They start overlapping at 1 minus square root 5 and they stop overlapping at 1 plus square root 5. So my overall solution then, the overall solution is bracket 1 minus square root 5, comma 1 plus square root 5. And the graph of the overall solution will just be the graph of where they overlap, which is the graph we already saw up top. Graph of 1 minus square root 5 to 1 plus square root 5. And that's all. Now these things take some time to get used to. You got to practice these because they do take a bit of time to handle. Without practice, you will not get good at them. So I encourage you to continue working on these, try numbers of examples, and then use Khan Academy and other resources to help you to understand the concept better. That's all for this video. All the best.